So today let's take a look at an interesting Chinese extension. It looks quite nice, it's quite small, portable, elegant, thin, nice looking. You can very easily fit it in your pocket. It's very aesthetically pleasing, decorative, and you can easily disguise the cable so you barely see it. It has a transparent, shiny cable, so beautiful, but it's a horrible death trap. I've got it from eBay from China. It cost me $1.40 including shipping, and it has a European plug. It's for any mains voltage, and the cable is 3 meters long. It looks nice, but the cable is super thin. And also this plug is smaller than a proper European plug. This is what I call a Chinese version of a European plug, basically. It's smaller. Basically the pins are the same, but this plastic part is smaller, and also the cable is much thinner. Here's the socket, and this one actually fits into it quite well, but the real European one doesn't really fit into it well. It actually barely makes a contact because there is a recess in it. It's hollow, but it's too small. This one fits into it, but this one doesn't. The recess in it is too small, basically. And the outer dimension of this one is what the inner dimension should be. It does actually make a contact, but it doesn't go all the way in because this hollow part of it is too small. It's made of a very soft material, actually. It's more like a rubber than a plastic, and here you can see the holes in it, the contacts, which are basically some like tubes, and the wire connected to it, a super thin wire. There is some stress relief on it, but it's super thin, and it looks like the cable is almost sticking out of it. And on the other side of it, it's about the same. The cable is off center in it, of course, quite a lot, and here's the connection. It says 250 volts, and the cable is connected to those pins, which are nicely plastic sleeved, so it looks safe, but it definitely isn't. And those pins look quite soft. Is it aluminum? It's a very soft material. I could almost snip it with my scissors. That's amazing. It looks like aluminum. It's very soft. I could almost chew it. And the pins are hollow, probably. The cable is very, very thin, and it doesn't look like copper. It's silver. So is it steel or aluminum? It doesn't seem to be magnetic, so it's probably aluminum. Or maybe copper with some plating, I don't know. And today I have a dog instead of a cat. So this extension looks nice, but it has several different problems. Firstly, it's called European, but the real European plug doesn't fit into it well. The second problem is that this insulation on it is super thin. It's definitely not a double insulated cable, and you can very easily damage it and get an electric shock. And the last problem is that the conductors in it are super thin, and it may not even be copper. It can be, for example, aluminum, which has a higher resistance. It probably has quite a high resistance. You can very easily overload it, it's gonna get very hot, and it may catch a fire. So there is a risk of electric shock, risk of fire. Very nice. The construction looks quite dodgy. So let's test it. I've got a lamp here for the test. Let's plug it in like this. My fire extinguisher is ready and let's turn it on. It works, but it's quite dodgy nevertheless. And now let's try to measure the resistance of the cable, because this is gonna reveal how dodgy it is. I guess the resistance is gonna be quite high. So let's take my meter and measure the resistance of one of the wires. 2.8 ohms. And the other one is probably gonna be the same. Also about 2.8 ohms. And the resistance of the probes is... it's actually 0. So let's do some calculations. Each wire is about 2.8 ohms. And it's 3 meters long. So the total resistance is gonna be about 5.6 ohms. So now let's try to calculate the cross-section of the wire from it using my secret formula. So the cross-section of the wire in square millimeters equals the length of the wire in meters divided by 56 times the resistance of the wire. And you put 56 here for copper or 35 for aluminium. So the cross-section is gonna be 3 meters. This is how the cable is long, divided by 56. Let's believe the cable is made of copper, and times the resistance. Now the resistance of the wire is 2.8 ohms. And let's do the calculation. And the result is 0.019 square millimeters. Seriously, the cross-section of the wire is 0.019 square millimeters. Are you kidding me, guys? And if it was aluminum, the formula is gonna give 0.03 square millimeters. So in any case, the conductor is super thin. And now let's try to see what happens if you load it. The maximum current of European appliances with a flat plug, this small one, is 2.5 amps. The voltage drop on it will be U equals R times I, and this is U equals the total resistance of it, 5.6 ohms, times the current, 2.5 amps, and this is 14 volts. Now the power dissipation of the cable is P equals U times I. So the power dissipation is the voltage drop, 14 volts, times the current, 2.5 amps, and this is 35 watts, which is quite a lot. And there is also my secret formula for a power dissipation of a resistor or anything with a resistance. It's a quick formula to calculate its power dissipation in just one step, instead of those 2 steps. This version is used if you know the current, and this one is used if you know the voltage. So now this one is gonna be useful, and the power dissipation of the cable is going to be its resistance, 5.6 ohms in total, times the current squared, 2.5 amps squared. And it gives the same result as before, 35 watts. Now the thing is that if you really want, you can also force this big European plug into it. And appliances with this plug are limited to 10 amps usually. This one comes from a vacuum cleaner and it has a lamp on it for indication, and I'm gonna show you that I can get it into it. And it makes a contact. So appliances up to 10 amps can be connected, and the voltage drop of it at this current is going to be 56 volts, which is about 1/4 of the mains voltage here. And the power dissipation of the cable at this current is going to be 560 watts, which is definitely going to be quite interesting. If this power is dissipated in this cable, you probably know what's gonna happen. And by the way, I like how those vacuum cleaner cables have those red and yellow marks on it. It's like the chain of an anchor. It's like if pulling the cable to the end of it is going to cause a nuclear explosion. It's like, warning, you are getting close to the end of the cable. Danger, you are getting very close to the end of the cable. But let's go back. This power dissipation is definitely going to cause a fire, but it may get even worse. What if you short it out? What if you plug an appliance into it which is in a short circuit? Because any appliance theoretically may fail short circuit, and you probably say, okay, it's gonna trip the breaker. But really? The problem is that the resistance of this cable is so high that a short circuit may not trip the circuit breaker. If it's in a short circuit, the current is limited only by the resistance of the cable, and the current is going to be the European mains voltage, 230 volts, divided by the total resistance of it, 5.6 ohms, and the current is going to be about 41 amps. Now the power dissipation of the cable is going to be the voltage times the current, and this is 9,430 watts. And this is just absolutely crazy. I can also calculate the power dissipation using my quick formula. It's second version. Calculating the power dissipation of a resistor, knowing the voltage on it. So the voltage on it is 230 volts squared divided by the resistance of the resistor or cable, and this is going to be, and here's the result. It's slightly different because the current in this calculation was rounded. So this one is more accurate, and this is how you calculate the power dissipation of a resistor if you know the voltage on it, in just one step. So the short circuit current is 41 amps, and you probably say, okay, this is gonna trip the breaker, but it may not be the case. Virtually every circuit breaker has two different ways of tripping. The first one is a thermal tripping, which is using a bimetallic strip. The current is heating it up and it's bending. Now this one actually works for a low overcurrent, but it's very slow. It takes a lot of time before the current can heat up this bimetallic strip and trip it. And just a very small overcurrent can trip it, but it takes a lot of time. And the second way of tripping is a magnetic tripping, which is using an electromagnet. There is basically a coil and the current goes through the coil, and if the current is too high, it will pull an iron core into it and trip the contacts. The magnetic tripping is very fast, but it requires quite a high overcurrent to trip, and this usually happens when there is a short circuit. And this one shows the tripping time versus the current. There are various types of circuit breakers, and the slow or thermal tripping is usually the same for all, but the fast or magnetic tripping is different according to the type of breaker. The most common breakers are B, C or D. The B type is tripping at 3 to 5 times the rated current. The type C is tripping at 5 to 10 times the rated current, and the type D is tripping at 10 to 20 times the rated current. This is of course the fast tripping or magnetic tripping, but all of those types are also going to trip at a low overcurrent, but it's going to take more time. In Europe, in households, the most common breaker is 16 amps and type B. It's this one, and it means that for a fast trip it requires 3 times to 5 times the rated current. And for 16 amp breaker it is 48 to 80 amps, which is quite a lot. So the threshold of a fast tripping is somewhere in between 48 to 80 amps. And if the overcurrent is lower, it's gonna trip using the thermal tripping, which is very slow and it may take several seconds or even several minutes to trip. Now, because the short circuit current I have calculated for this one is just 41 amps, it's not gonna trip the magnetic part of the breaker, and it has to trip only the bimetallic strip, which is very slow and it may take multiple seconds before it trips. And this is the reason why having a short circuit at the output of this one may get quite interesting. A proper extension should either be able to handle the full current of the breaker, or it should have a lower rating breaker or fuse built into it. which is definitely not the case in this one. So this is enough of a theoretic science, and now there's time for some stupid experiments. So here's the extension, here's my appliance, which just accidentally fails short circuit, and I can also measure the short circuit current. And here's my circuit breaker. So the experiment is ready. I'm setting up 2 cameras because there is just one try, and of course the dog is locked out. So let's try to turn it on, and don't try this at home. 3, 2, 1. You, 1. So the breaker didn't actually trip. So what happened? It's kind of blackened. Also my extension is a bit blackened. My clamp meter is okay, luckily. It has a lot of black spots on it where the smoke was coming out. And where's the open circuit? I think I can see it. It's here. Here it failed to open circuit. It acted as a fuse, basically. And there is quite a lot of black spots on it. Some pieces of the wire are sticking out, like this, and that's it. Should I try to fix it and give it one more try? Of course. Let's reconnect it and let's go. 3, 2, 1. Open circuit. One more fix. 3, 2, 1. So as you can see, it can create a lot of special effects. So the meter didn't show the 41 amps I calculated, but this may be because its refresh rate is quite slow. And when I turned it on, the current went up, but then because the wire is heating up, the resistance goes up and the current goes down. Because almost all metals, when heated up, the resistance goes up. And so the current goes down as it heats up, until it actually melts and loses connection and the current disappears. The refresh rate of this one is not very fast, and in the video it was showing 0, then 27, 22, 14 and back to 0. So it basically takes samples in some intervals like this. So it could be like this. For example, 0 amps, still 0, then 27 amps, 22 amps, 14 amps, and when it loses connection, back to 0 amps. So it doesn't actually have to measure the peak here, and this one still could have been 41 amps as I calculated. When I scratch it, I can see some traces of a coppery color, but also some traces of a silver color. And it's completely non-magnetic. So is it some alloy of steel and copper? I don't know. For a pure copper, it's just too springy. One conductor is made of 8 wires. So let's measure the diameter using my vintage tool. The diameter is 0.1 millimeters. Now let's calculate the cross section of it. The cross section is pi times the diameter squared divided by 4. And this is about 0.00785 square millimeters. But because there is 8 wires, I have to multiply it by 8. So the total cross section is 0.062 square millimeters. So here is the total cross section, and now let's try to calculate the conductivity of the material. So now the conductivity of the mysterious material in megasiemens per meter is going to be its length in meters divided by its resistance in ohms times its cross section in square millimeters. So its conductivity is going to be 3 meters divided by 2.8 ohms, which is the resistance of the wire times the total cross section. And this is about 17 megasiemens per meter. So here you can see the conductivities of some common materials, and the conductivity of our material is actually less than copper and also less than aluminium. It's close to the conductivity of zinc, but it's probably not a pure zinc. It seems like it's an alloy of some of those. So this is Diagon Wild, and see you in my next videos. And thanks to all of my patrons on Patreon. I really appreciate your support. And of course, a flame test.